Have you ever been in a brand new situation, maybe a negotiation or a game, and had no idea what the other person was going to do? You can't predict their exact move. But what if you could predict how a rational person would think? Well, today we're going to unpack the logic of rationalizability. It's a really powerful way to think about how other people are thinking.
All right, to get our heads around this, we're going to use a simple but kind of brilliant puzzle from game theory. And this one little game is going to be our guide through this whole explainer, showing us step by step how rational thinking actually works.
So, let's set the scene. Imagine you and a total stranger have to split $4. That's it. Your only job is to decide how much you're going to demand for yourself. So, what's your first move? What do you ask for?
Now, the rules are pretty straightforward. Both of you announce a whole number, anything from 0 to 4. If what you both ask for adds up to $4 or less, great. You each get what you demanded. But if the total goes over 4, you both get hit with a penalty and walk away with less. And of course, the goal for you is simple: get the biggest payout possible. Okay, this grid might look a little intense, but don't worry. Think of it as a map of every single possible outcome. Your choices are on the left, your opponent's choices are up top. And in each little box, that first number, that's your payout. The second one is theirs. This is the whole game, laid out right in front of us. So, let's start analyzing this, but let's start simple. Let's just think about our moves. We don't even need to guess what our opponent will do just yet. We just need to figure out what makes sense for us as a rational person.
And what do we mean by rational? It's actually pretty simple. A rational player just looks at the game, forms some kind of idea about what their opponent might do, it could be anything, and then picks the move that gives them the best possible outcome based on that belief. That's it. So as a rational player, the very first thing you're going to do is scan for moves that are, well, just obviously bad ideas. No matter what you think your opponent's going to do, some of your own choices are just never, ever the best pick. And this table shows it perfectly. Just look at your options. Demanding $0, you're always going to get 0. And demanding $1, well, if you compare that to demanding $2, you'll see that asking for 2 is always better or the same, no matter what your opponent picks. So there is literally no world where asking for 0 or 1 is your best move. A rational player would never do it, so let's just cross them out. So we've gotten rid of our own irrational moves. Easy enough. But this is where the magic really starts. We aren't just a rational player, we're going to assume that our opponent is also a rational player. And if they're rational, they just went through the exact same thought process we did. Okay, so if we know they're rational, we can confidently cross out their irrational moves too. We know for a fact they will never ever demand 0 or $1. And just like that, the world of possibilities gets smaller. We don't have to worry about those first 2 columns anymore. The game just got a whole lot simpler. And this is where it gets really interesting. Knowing their rational changes our rational choices. Take a look at your options in this new, smaller game. If you know for sure they're going to demand at least $2, is demanding 4 still a smart move? Not at all. In every single one of these remaining scenarios, demanding 4 gets you a worse payout than other options. So we eliminate demanding 4 from our own list.
And we can go one level deeper. Our opponent knows that we're rational and that we've followed this logic. Just like we got rid of demanding 4, they do the same thing for themselves. They know we won't demand 0 or 1, and that leaves them with only 2 choices, demanding 2 or 3. So let's look at our options one last time. If they demand 2, our best move is to demand 2. If they demand 3, our best move is still to demand 2. At this final stage, demanding 2 is the clear winner. It's the only move that survives.
This whole powerful step-by-step process, this I think that you think that I think loop, it actually has a formal name in game theory. It's called rationalizability. An action is rationalizable if you can justify it at every single level of this logical spiral. It's a move that makes sense based on what you think they'll do, which in turn makes sense based on what they think you'll do, and so on forever. It's the set of actions that can withstand all of that logical pressure. Now that whole I think you think thing can feel a little bit like a hall of mirrors, right? It can make your head spin. Thankfully, there's a much more direct, almost mechanical way to find the exact same set of answers. So instead of getting all tangled up in beliefs about beliefs, we can just reframe the whole thing as a simple process of elimination. It's a different way to think about it, but as you'll see, it gets us to the exact same place. And the key concept here is what's called a strictly dominated action. It sounds technical, but it just means an action is strictly dominated if you have another option that's better in every single possible scenario. It's a move you would literally never make. Remember back in our game how demanding 0 or 1 was always a bad idea? Those were strictly dominated actions. And this gives us a simple, repeatable process. Step 1. Scan the game and cross out any of those strictly dominated, never best actions for everybody. Step 2. Look at the new, smaller game that's left over and do it again. You just keep repeating this until there's nothing left to eliminate. And whatever actions are left standing at the end, those are the rationalizable actions. It's the same logic, just turned into a simple algorithm. So what does this tool really give us in the end? Well, it tells us the boundaries of logical play. But it's really important to understand what it's predicting and maybe more importantly, what it isn't. Now, if you've heard anything at all about game theory, you've probably heard of the Nash equilibrium. It's a hugely famous idea, and it's crucial to understand how it's different from what we've just been talking about.
Here's the difference. Rationalizability gives you a set of plausible actions. It's saying a logical player might do any of these things. A Nash equilibrium is much more specific. It predicts a single, stable outcome, a combination of moves where nobody wants to change what they're doing. Think of it this way. Rationalizability is for a brand new game, but Nash equilibrium is for a game that's been played over and over again.
So here's the relationship. Any move that's part of a stable Nash equilibrium is always going to be rationalizable. It has to be. But the reverse isn't true. You can have a bunch of rationalizable actions that aren't part of any specific equilibrium. The real value here is that rationalizability maps out the entire universe of what's logically possible when people are just thinking things through from scratch. You know, the game theorist Martin Osborne put it perfectly. He said that rationalizability predicts the actions of each player, while a Nash equilibrium predicts the profile of actions for the whole group. One is a set of individual possibilities, the other is a single, stable group outcome. And all this leaves us with one last big question. We have these amazing logical tools that can map out the absolute boundaries of rational strategic thinking. But does knowing what's perfectly rational actually make messy, real-world human behavior any more predictable? That's the real puzzle, isn't it?